So we discussed yesterday that one of the downsides to Newton's method is that you'd have to be able to evaluate the derivative. Okay. Well, we can make a slight modification to this, and is what we'll actually call this is the modified secant method. And I'm going to move this timer here so that I can write in that location here in a minute. But here is our equation for Newton's method. Okay. And here is one way. There are many slight modifications to this that we could use to approximate the derivative at x sub I, but this is one of them. And is what's going on here is in the numerator, we have our change in y, and then over our change in x. Okay, and you can see the change in x right here. Okay, right. This is, we're using delta times x sub I. Okay. And so you'll want to choose delta to be small, but there will be a balance. If you choose it to be too small, we might end up with some bad round off errors. But if we choose it to be too large, we also might be, it might take too long to converge. Okay. Or it might be inefficient. That might be the better way to word that. Okay. Well, we want to combine these two. Let's go ahead and do that. Okay. So if we're going to combine these, all we're really going to do is replace this f prime of x sub I with this blue formula here. So x sub I plus 1 is equal to x sub I minus f of x sub I over this. Okay. But now remember, if you are dividing by a fraction, that's equivalent to flipping it over and multiplying, okay, or multiplying by the reciprocal. So in fact, what will happen is this delta x sub I will end up in the numerator, and this f of x sub I plus delta x sub I minus f of x sub I will end up in the denominator. And so what we're going to do next is we're just going to go into MATLAB. We're going to replace really this equation right here with this new one, because this one doesn't involve the derivative. Okay. Now that we're in MATLAB, you can see I've named this MODSEC for modified secant, so I need to change the name here. All I've done though is I've copy and pasted our Newton's method code here. We're just going to make some slight modifications. So mod secant. And I use capital M, capital F, S, and that's up to you if you want to use capitals there. It doesn't really matter. And since we're not going to need the derivative, why don't we get rid of that comment and maybe write delta. Okay. And so delta is just going to be some constant that we choose in order to approximate that derivative. I should say to help. It's not this number in itself that's going to do that. Okay. And so I'll go up there and replace defunct with just the word delta. And I think that all looks good now. Okay, well, let's go down and we are going to edit that one line, this one right here. So remember, in the numerator now, we're going to have three things. We're going to have the function value at x sub r, but then times delta, and then times x sub r. Okay, we were using x sub I, but this is the same idea here. Okay. And then in the denominator, we were going to have, it was func of x sub r plus, okay, plus our delta times x sub r, and then this was minus f of x sub r. Okay. All right, and that looks good. Let's go ahead and save this, and then we'll give this a run. Okay. And again, we'll just use the bungee example since we already know what the root is. In fact, you can actually see what the output's going to be here in a second. Let's go ahead and hit bungee, and maybe I'll just clear this so we can see that it actually pops up. Okay. All right. And so I'm in here, and I've actually already typed in mod seek, and then we have our function f, and then the second input, if you remember, we said we were going to make that second input, rather than defunc, we were going to make it delta. And so if I go back to my bungee example, my delta, I just chose 0.2, something small. Okay. And then we need just an approximation of the root, and so we're saying, hey, it's close to 130. Okay, so let's go ahead and run it and see whether we have any errors or not, because we could have made a typo. Let's see. Okay, looks like we have made a typo, and I already see what it is. You see how I have func of xr, func, but then I just wrote f. Let's go fix that in our modified secant function. Okay, so func. I'm going to save, and then we'll try and run it again and see if we end up with any other error messages. Okay, no, we didn't. There's our root. It's approximately 142. Okay, so this seems to be working just fine. And we could compare this with what we got with some of our other techniques, like maybe we'll actually use Newton's method. See how these compare. So we called that Newt RAF, okay, and we needed F and DF and the approximation. Okay. So we'll get to see these two side by side. Okay. And so it looks like they're all the same up to this point. Okay, so this is pretty accurate. In fact, if we wanted to, we could even subtract these two values to see how close they are. Okay. Why don't we do that? I'm going to say minus and let's just take the absolute value of it as well, because we don't really care whether it's positive or negative. We just want to see how close they are. Okay. Yeah, so these are very close, right? The difference between these two is 0.00006842 and so on. Okay, so it's worked pretty well. And again, the whole benefit to modified secant is we don't have to rely on the derivative, because as you saw in this example, the derivative was definitely not impossible to take, but it would be challenging. It'd be easy to make a mistake in taking that derivative. But there are some derivatives we just won't be able to take, and so this will be what we have to do.